All right, so podium construction is very popular for mixed use and residential application, particularly in California, for cost and speed. And there are basically two types of projects that we do. There's type 5 construction over a concrete podium and type 3 construction. Type 3 construction would allow for a larger building and a taller building, so that's typically 5 levels over the concrete. And there you're using fire-treated wood. The podium itself can be 1, 2, or 3 stories above grade. The challenge as you increase the number of stories is going to be meeting the 2-stage analysis requirements. Because if your podium gets too tall, it's going to become more flexible, and it'll be harder to meet the requirement to be able to do a 2-stage analysis. And if you can't do a 2-stage analysis, you're going to end up putting the mass of your concrete podium into your wood superstructure, which will not be feasible for wood construction. The podium itself can be conventional, mild reinforced concrete slab, or it can be a PT slab, and I'll go over the differences here. PT slabs, very economical for multi-story residential and parking, especially if you've got a regular grid layout and multiple floors. You get some economy of scale. You can reduce slab thicknesses significantly, especially if you've got parking and or residential live load where you're talking about 40 or 50 pounds per square foot. When it comes to an actual podium where you're placing a 4 or 5 story building on top, the loading is significantly higher than you would have like in a traditional, like a high-rise concrete building. And so there you're not going to get that big of a decrease in slab thickness when you do PT. PT also, we can do longer spans. We can have longer cantilevers. And because the slab is tensioned, there's going to be less cracking. The drawback is that with a PT slab, making modifications to it in the future, you need to always scan it, to locate tendons before you core and drill. So on our projects in Southern California, usually in a mixed use project where we have commercial and retail use, the client does not want to have a PT slab because the tenants change. It could be a restaurant. They're going to core lots of holes. And as the tenants come and go, they all make modifications. And they don't want to have to go back and scan the slab every time they do that. The other problem is with a podium, you typically have irregular slab geometries. You've got steps in the slabs and depressions, and all those are a little more difficult to design in detail if you're doing PT. And that's, contrasting with like a mid or high-rise concrete building with PT slabs where you've just got a flat plate that repeats. It's a lot simpler to do that design. The basis of the podium is that we're going to be able to do low-cost wood construction on top of the concrete podium, and we do that with this 2-stage analysis procedure. Most people just take it for granted that they're going to be able to apply this, but you do technically have to check. I've had trouble, especially with double podiums. It's turned out to be really, really close that we actually meet this requirement of the podium being stiffer, 10 times stiffer than the wood superstructure. So that will kind of be a function of how open the floor plan is on the podium level, because a lot of times, the architect is thinking that it's, pretty much an open floor plan at the podium. They don't give you a lot of shear wall to work with. And then if you don't have enough stiffness there, and typically also the podium level is taller, right? So you have kind of like a soft story condition, then your stiffness may not be actually meeting this requirement. So you do have to be mindful of this. When you get to a triple podium, it's even harder. And I've seen a lot of engineers, they've got different tricks for trying to meet this requirement. But just check it before you promise, doing too tall of a podium. When you size the podium, you start by using the prescriptive 2-way slab thickness from ACI 318. So on the slide here, you can see that if you're using grade 60 mild rebar, there is a span to thickness ratio that they recommend. So if you look at the column without drop panel and you look at an exterior panel or an interior panel, you're looking at span divided by 30. So if you had a 30-foot grid, then that would be a thickness of about 1 foot or 12 inches. And typically you're going to try to get your podium to work without drop panels and without edge beams and interior beams. It's usually a flat plate. So that's kind of where you start to get your preliminary sizing. Then you have to determine the load from the superstructure. When you do your initial sizing, I recommend that you do not reduce the live load. So, think, for example, if you've got, 5 levels of residential framing, that's 40 pounds per square foot on each of those levels live load. That just adds up. So when you do that initial analysis, I would recommend that you do not reduce that. And remember to consider all the other load that you might have. Something that's often overlooked is the topping slab thickness, or if your podium is having a variable thickness because it slopes to drain. So your podium might be 12 inches thick at the low point at the center of the courtyard, but it might be 18 or 20 inches thick, at the edge of the courtyard, and that's going to add a lot of mass to your structure. The special loading that you'll consider in the design of your podium will be point loads from the columns, which you'll typically have at like transfer areas, your tie down reactions from your shear walls, landscaping, planters, trees, fire truck loading, and then another thing that comes up is construction loads for cranes, man lifts, forklifts, that kind of thing. As you get into the design, you're going to then have to figure out whether you need drop panels. And this is the first kind of technical area that I want to get into. A drop panel has a very specific definition in ACI 318. And basically, a real drop panel is sort of a flexural drop panel. It basically will increase the flexural stiffness of your slab. But in order for you to reduce the amount of flexural steel you have in your slab, you have to meet the minimum dimensions in this code section. So if you see part B there, it says that the drop panel shall extend not less than 1/6 the span in each direction. So if you had a 30-foot bay, you would need your drop panel to be at least 10 feet square, and then it would be considered a flexural drop panel. If it was less than 10 feet square, and we're typically using 6 or 8 foot square on our projects, then it would be more of a shear cap, or just, in other words, only used for punching shear and not for reducing the flexural stiffness and strength of your slab. And the reason why this is important is because SAFE does not know that. So when you model a drop panel in SAFE, it's going to account for that stiffness, and it will adjust the amount of reinforcing that when it designs the slab for you. So in the old days, this is how they would build to a slab. So you can see there's sort of a conical column capital and then a drop panel that goes around it. And then, in more modern construction, a column capital would be square because it's easier to form, and typically just placed to handle punching shear. But if these were going to be used as flexural drop panels, they would have to be much larger to meet that span over 6 ratio. And then here is a real flat slab where we're using stud rails instead of drop panels. And this photo is also taken from the Varial project. Here you can see the columns are they're very rectangular. And the reason for that is because these extend into the basement and through parking levels. So the columns have been optimized to fit between parking stalls. When it comes to designing for punching shear, SAFE has a module. It's very generic though, and it might tell you, for example, that you need 7 stud rails, but for a square column, you're probably going to have an even number. We also use Decon stud rail, which is proprietary software. Their design is more conservative, but they are in the business of selling stud rails, so it kind of makes sense. So, you know, an economical design might be somewhere between these two. The stud rails themselves, what'll come up during construction is whether you can install them upside down. You know, a stud rail, if it's installed after the mat reinforcing is put in place and they haven't put the stud rail in, it's kind of hard to get it into place. So a lot of times they like to just set them upside down, and that's usually acceptable. This is a photo of a built-up stud rail. So this was placed at an area with high loading in a drop panel. So there was a drop panel and a stud rail, but nobody really manufactures stud rails that are tall enough. So they weld studs end to end like this, and then they bend test them to show that they meet the strength requirement. So this is just kind of an interesting photo that shows that.
A quick question. Is common practice over there in the West Coast to do puddling at the columns, meaning higher concrete strength around the column versus the slab, or that's something you guys?
Yes, it is. Okay. It is. Mm-hmm. Yeah, so typically the columns are going to be higher strength concrete than the slab. And ACI even has provisions that kind of limit that delta between the slab concrete strength and the column, because typically you pour the column and then once that's done, you come and you pour the floor, but the floor is a different strength concrete. And then you pour the column on top.
I mean, like the drop panel area having a different concrete strength from the rest of the slab, not the column itself.
No, only the column. The slab and the drop panel would normally be poured with the same strength as the slab itself.
In Florida, also for like high-rise flat plate, we used to do a lot of puddling, meaning we'll pour
letting it like overflow out
10,000 psi slab area, and then the rest of the slab, you know, whatever 5 or 4,000.
Yeah, I think that definitely comes into play when you're talking about high-rise construction, because then you've got much more demand on your columns. But usually, you know, for podium columns, the loading is pretty light, so they're not generally even very heavily reinforced columns at all. You know, not much more than minimum, really.
Yeah, all right, thanks.
No problem. The next area I'd like to talk about is deflection for podiums. So there is a serviceability requirements in ACI. This is just a sort of an excerpt. It's pretty typical, you know, immediate deflection L over 360 and total L over 240. But what you have to always consider is the long-term deflection. So using this formula, you end up basically, if you've calculated the elastic initial deflection, you're going to take that number and generally multiply it by 2 or 3, and then that will give you your total long-term deflection. So when you're designing concrete elements, don't be fooled by, you know, the initial deflection output you get from Intercalc or any of the programs we use, because that's not going to consider the long-term deflection unless you've set the program up to analyze that for you. And typically when we do podium design in SAFE, we do take advantage of SAFE's cracked and nonlinear analysis to calculate the deflections for us. This is just a plan view of a typical camber plan on a podium project. So we would set cambers basically to cancel out the dead load deflection at the critical points where they can actually control the elevation of the formwork that they're placed in the Decon. And usually we're only calling out cambers if you know, starting at a 1/2 inch or more. Reinforcing plans. We usually show the reinforcing in different directions on separate plans because they tend to get congested. And we call out sort of a typical reinforcing, and then all we show on the drawing is the added rebar. So typically we're adding rebar, maybe, you know, bottom steel near center spans and top steel where there's negative moment and at columns. And then another thing to consider is if you do have depressions, that you show your rebar with a kink in it if you want them to provide rebar through that depression. If they're small depressions, like less than an inch, usually you don't do that. But if it's a large depression, 4 inches or 6 inches, and you need your rebar to pass through, you either have to provide a special detail where you're lapping bars at different elevations, or where you're going ahead and bending the rebar at a 1 to 6 slope to pass through the depression. If you miss that, you might be facing a very large change order during construction. This is a photo of what the reinforcing looks like before they pour. So you can see they've got all the rebar, it's 2 mats, top and bottom, and they've laid out where the walls of the superstructure are going to go. So there's, sill plate anchor bolts and tie down rods. And in the photo on the right is an actual hold down in a corner condition. So it's kind of hard to tell, but if you see in the corner there where the 2 plywoods meet, there's 2 anchor rods, one on each side. And then if you look into the rebar, you can see there's some bars at a 45-degree angle. Those are the supplemental reinforcing bars that restrain the breakout area around the tie-down rod. Our tie-down reactions, they can be anywhere from 40 to 70 kips. So it's a really huge force. So we generally have to add a lot of reinforcing to restrain that breakout and, keep it into the slab. Now I will transition to the safe model. This is just a screenshot from the Vario project, kind of showing the podium and the extents of the shear walls and the drop panels. Let's see here. Can you guys see the screen? So this is a very simple model that I put together just for the purpose of this presentation. And what it is a rectangular slab with walls on 2 sides. So that could be, basement walls, or they could be, basement retaining walls or shear walls. And then I've modeled a couple of different conditions as far as, no drop panel, a larger drop panel, a small drop panel. And then I've also thrown in if I extrude here, I've thrown in an area of the slab which is dropped down from the rest of the slab. And I just wanted to demonstrate some of the, modeling features in the program. On the screen, you can see this little R symbol. This is a release in the slab that you can model. The release allows you to release the moment in the slab so that the program will not consider the slab continuous through the joint. And that's how you're able to model, for example, a slab depression. Or if this was a parking level or a parking garage and you had a sloped ramp, you could have the slab and then put a release between the 2 right where the ramp is, because the structure doesn't actually connect there. And then let's see if I can show you the column strips. These pink lines are the column and middle strips. The program can auto assign the width, or you can do it yourself. Usually in a typical project, you might not be able to get a very nice column and middle strips. You have to use some engineering judgment in defining your middle strips. You might have 2 columns that are very close to each other, and perhaps you combine them into a single middle strip, or a single column strip. And the program will integrate, the finite elements along that strip to give you the reactions and the amount of reinforcing that you need there. And let me show you the design here. If I show you the strip forces, you can see this area where I've defined the releases. The moment in the slab is 0 at the release, and then maximum at the center. Whereas in the areas where the slab is continuous, you have positive and then negative moment, right, alternating. For the connection to the basement wall, I've also modeled two conditions. Along grid line 4, I've modeled fixity between the slab and the basement wall. And then on grid line F, I've modeled it as pinned. And I just want to let you know, in case you see that I've modeled something differently than you may have designed something in the past, it doesn't necessarily mean that your design is wrong or unsafe or anything like that. It'll just change the way that the forces are distributed in the slab. And as long as your reinforcing reflects your design methodology, everything will be fine. So when you pin the connection between the slab and the wall, your design will tell you you need more positive reinforcing in the slab, right? Whereas if you're relying on that fixity, then you're going to need more negative reinforcing at the slab to wall interface, but the trade-off is you need less positive reinforcing at the center of the slab. This will come to play when you're looking at your detail between the slab and the wall. So typically you would pour a wall first and then pour a slab on top of it. The slab would be bearing on the wall, and then you would have dowels coming up from the wall to go into the slab. But a lot of times the wall continues to another level, and they want to pour the wall straight up and then have the slab, have the control joint or the construction joint be on the vertical face. So it's a slightly different detail. And if you're counting on using that steel for resisting your negative moment in your slab, then you can't also be using that steel for shear transfer, for your diaphragm forces, or for even shear friction if you're relying on a vertical cold joint for transferring the gravity forces into your wall. So you may need more reinforcing if you're designing it this way. Then I can show you punching shear design. So basically anywhere you've defined a beam, it's not going to calculate punching shear, so you'll see an NC. And then where I modeled nothing, it tells me that my punching shear ratio is, way over 1, not going to work. Here I have a larger drop panel. My DCR is less than 1. And then on grid line 2, I just modeled different shear stud configurations. And you can see that grid C and 2, it's basically telling me that I need 5 rails. But again, when you schedule that and put it on your drawings, you're going to have an even number of rails. For punching shear DCRs, I recommend that you keep them around 85%, unless you're able to coordinate very well all of the electrical and plumbing penetrations. So typically through a podium, you're going to have storm drains and electrical conduit and sewer lines, and architects like to bring those down near columns, so they're going to pass to your column capitals and your drop panels. So unless you've explicitly accounted for those penetrations and the reduction in your punching shear capacity, you want to have a little bit of a reserve there so that when you get the RFI later, you're able to justify that and not have a punching shear problem. Then, let's see. For slab design, typically you want to find a sweet spot of your typical reinforcing and then just have the program output the additional reinforcing you need. And in that way, it's easy to put together your reinforcing plans. And what I like to do that also helps during construction inspection is I'll have my typical reinforcing be one size, and then my added bars at columns be a different size, a larger size. That way it's easy to count the number of added bars that are being added. For deflection, I have another model, and I've already run it because what I've done is I've defined these special nonlinear static load cases. And this is just following SAFE's best practices for modeling the correct behavior of the slab. So the first load case is basically a nonlinear load case that considers the correct properties of the concrete. And in order for the program to work accurately, you do have to tell it what your reinforcing is. And if you look at the definition here, it's basically the dead load, the superimposed dead load, and the total live load. The second load case is the dead load and the superimposed dead load, but then only the probable live load, sort of the constant live load, right? Not your worst case live load. And that's usually around 25%, could be less, because the odds of you being at your full design live load all the time for the purpose of calculating deflection is unlikely. The third load case that you need to define is a nonlinear load case, specifically looking at the creep and shrinkage. So you define the creep coefficient that comes out of that table in ACI that I showed you earlier, and a shrinkage strain. And it's the same dead, live, and probable live that's defined here. And then there's a fourth combination, which is only the dead load and the amount of the superimposed dead load that the structure sees by the time that you start to load it with construction of your superstructure. So this is like maybe only 3 months into construction. So because of this being only 3 months into construction, my creep coefficient is much smaller because it's a shorter term analysis. So when you have those 4 cases defined, then you can define a combination which will give you your camber, which is basically adding the first and the third and subtracting the second and the fourth. And then that will directly output your what you should camber. If you only want to know the total long-term deflection, you only need the first 3 load cases. You don't have to subtract out that initial deflection that occurred in the first 3 months of construction, right? Because it would have already happened by the time you start to install your superstructure. And that usually, let's see if I can. So once you start doing nonlinear analysis, it takes a lot longer for the program to run. But it will give you these nice contours. And when you look at your model, you'll be able to tell, if your meshing makes sense and if your boundary conditions are correct. So that'll help you diagnose problems. So I do recommend that you spend some time to look at that when you're doing the first pass on your model.
Yeah, Phil, can you load the camber combinations again?
The camber combination. This one.
Mm-hmm. Hmm. Yeah,
so I can reply.
That one a little bit.
Yeah, I can reply with a link for you guys to the long-term shrinking creep and shrinkage load combination. Back to the old-fashioned way of doing it, you can just take your initial elastic deflection and multiply that by 2.5 or 3. But what you'll find is, specific to your project and your exact reinforcing and your slab thickness and your concrete strength, that that number could vary a lot. And I'm finding that usually I'm getting a little bit more deflection with this analysis than by using the more prescriptive method in ACI. But I'm also trying to push the spans and keep the reinforcing as light as possible.
All right, thank you. We can talk about that, later on.
Let's see. So when it comes to actually modeling, I know a lot of people are big fans of the null areas, but I've done some really complicated podiums, and what I found is there's a lot of graphic display flaws with the program. So it, you know, when you start having a bunch of overlapping null areas with different loading on them, the colors start to get messed up, and sometimes it just won't display the accurate loads, and you don't know if it's a graphics problem or a modeling problem. So for that reason, nowadays I specifically model every piece of slab with a different loading as its own element, and I'm basically manually mesh them together, as opposed to drawing, you know, a big flat plate and then a bunch of null areas that overlap with each other. So, you know, if the null areas have been working for you, then I think you can continue to do that. But I've learned the hard way that it's not worth it, because I spend hours trying to fix models where, you know, you look at the deflected shape and there's a piece of wall that's flopping away from the slab and just can't figure out, or even in the slab, you'll see a break in the slab. And it's all because of the way the program does the meshing. So it's possible to lose accuracy there. So sometimes you've got to change your analysis method and use the standard solver, which takes a little bit longer, and then you've got to read through the whole report to find out what anomalies are in the model, and it'll output all the coordinates where, you know, nodes are not connecting. But it's very tedious, especially if you're, you know, far down the road and you have a very complicated model. You don't want to have to go back and, you know, fix 100 nodes one by one. Under cracking analysis, this is where you would define the reinforcing you want the program to use when it checks those cracked load cases for you. And then when it comes to defining things like drop panels, the program allows you to define them, right? So there's a type here. When you select the type, the program has an order of preference, right? So a drop panel will take precedence over your ordinary slab definition. So when you model a drop panel element over a slab element, the drop panel element governs. So that means if you had a 12-inch slab or a 16-inch slab, but you had modeled a 12-inch drop panel, the program will only consider 12 inches over that area, even though they overlap. So keep that in mind. It doesn't double them up. It doesn't add them together. It doesn't double the mass. Nothing. It just has it just sets the order of operation based on the definition. And then if I show you the punching shear again, let me change. The design details for punching shear is pretty detailed. I've gone through and validated the output here by hand, and I was able to match everything pretty perfectly. I've done the same thing for Decon stud rail, and that's why I know Decon stud rail is a little conservative. But there are limitations to this module, especially if you have you wanted to do a punching shear calculation adjacent to an opening, or you have some weird geometry, then it may not calculate the correct punching perimeter. But then you can always, you know, pretty quickly do that adjustment by hand to do the design yourself if that's the case. Let me see. There's a crack width module, which is pretty cool. It draws the contours and kind of estimates for you how wide cracks should be. So I imagine you can use this if you wanted to do some forensics on an existing structure. I've never actually, used it on a real project, but it seems like a neat feature. And I think that's it. Any questions?
Hello, Philip. Just a few things. This is Carla Binader.
Yep.
How's it? So a few things that I from using Safe. First, for the punching, I didn't get a very good experience using it, especially with irregular shapes. I've used before a punching Excel that we had created like a long time ago. I think it would need to be validated, but I think it's much more handy for special cases.
For special cases, yeah.
Yeah, especially since sometimes we don't use Safe. You do a hand cut.
And yeah. The punching shear module in Safe, at least for stud rail design, is definitely a newer feature for us. And that reminds me that you brought it up. Another thing to consider when you're detailing shear studs is a lot of times you have columns along the perimeter of the building. And if you're going to put a drop panel there, that could have an architectural impact. And then, it's not uncommon to have a column adjacent to a balcony where you might have a slab depression, or adjacent to the courtyard in the center of the podium where there are slab depressions. And in that case, your drop panel heights may be different. So your punching shear area would be different. And even the stud rail heights from one side to the other side of the column may be different. So you'd want to, pay attention to that when you're detailing and scheduling your punching shear reinforcing.
Mm-hmm. Thank you.
Bindu, you have any questions?
No, I'm
you see anything you can mark it?
Very informative. It was very informative. Thank you.
Hey, Phil, this is Danny. How do you typically address seismic loads coming down to the podium from the wood frame levels onto the slab?
Oh, great question. Yeah. So for that initial sizing, initial design, you haven't necessarily designed your superstructure yet. You don't know where all your shear walls are. You definitely don't have your reactions. But what we found is, especially by not using that reduced live load, that our slab reinforcing, the total tonnage of rebar is going to be pretty close. Later on, when we input the reactions from the tie downs, what I found is some areas do need a little extra reinforcing because of the concentrated point load. But that my overall reinforcing doesn't change much. It's pretty consistent, which is good. But that's only sort of been a coincidence that it's worked out that way. But I do think that if you've got the time and the budget, you should be modeling your line loads from your bearing walls and your concentrated forces from your tie down system.
Hey, Phil, this is Mike Campbell. Could you show us how you modeled that release at the slab depression?
Oh, yeah. So this is a trick I actually learned from Danny. Let's see here. So you can basically model a beam element. And then when you select that element, there under the properties, there is a line release. When you click the release, you can define a shear release or a moment release. And you can define that on either side of the line. Once you define that release, then the program will cut it off either for shear or moment or both, depending on how you define it. Does that make sense?
Yeah, great. Thank you.
So that I think will help you a lot, because before I knew about this, I would always just take a separate model, then model another little piece there and treat it as a giant opening. But now I can keep it all in one model. It's a little simpler from that perspective. And then, but after you run your analysis, you still take a look at the the moment and shear diagrams to make sure that it's doing what you expect. Because like I said, you will run into problems where the program is not meshed correctly, and it will dump the load from a floating node into something that shouldn't have any moment, and that's going to be a modeling error. You can also you can also define the offset. So let's see here. You see how under the assignment there's a vertical offset, and there's a definition there. So that's how I was able to graphically, I can move the slab relative to the rest of the structure is through this function. Similarly, with a beam, you can control the cardinal point for the beam. So you can define whether that center line analytical model is at the center of your beam, at the top flange of your beam, the bottom flange of your beam, at the centroid, and then the program will adjust for how you define it. And then you can always check if it's working properly by looking at the 3D extruded view. Yeah, because sometimes it just doesn't work, and you won't know that until you check out the graphics.
Phil, could you discuss a little bit about, we've talked about the analysis. If you could talk a little bit about what you see in the field with, in terms of podium design, about how do the cambers come out, and you mentioned the additional reinforcing for the hold downs, and how does that work out? Do we have a standard detail, and is that detail can just be used for all projects, or do we need to modify it? And what? Yeah,
so I think we're getting really close to having what we would consider to be a good typical detail for the tie down anchorage. That I don't know if anyone saw the invite. Simpson's doing a presentation on tie down anchorages soon, but there's now they're starting to use grade 354 BD anchor rods, which have a yield of 150 KSI. They're very high strength. But in ACI, if you go to the anchorage to concrete section, you're limited to 125 KSI. So you can't even really, as far as anchorage to concrete is concerned, you can't even really consider that higher strength. But typically that interface, the code will tell you to design for overstrength. But the second sentence is, or the maximum load that can be transferred to the structure. So basically, you want to make sure that tie down system is yielding above your podium. So a lot of times how we've achieved that is we will have a higher strength anchor rod into the podium, and then we'll step down to an A36 rod in the tie down, but a larger diameter. So it has the same strength, but it's going to yield before the higher strength rod. In the field, we've had, a fair amount of problems with them missing supplemental reinforcing. So what I recommend is that when you do that first site walk, that you really do have to kind of play inspector to save yourself the headache of fixing missed hold downs later, because it's very difficult to do. If it's a true above grade podium and you're missing a hold down, you can do a through bolt, right, with a large bearing plate. That may work. But if it was missing into just like a mat foundation and you have no access to the inner side, it's really hard to do. You have to blow out a very large area of concrete, epoxy dowel, a ton of stuff, because like I said, the force could be as much as 70 kips. So it's a really huge number to be able to justify that it's going to work. The other problem is when you're near an edge of slab, it's going to be hard to meet the minimum clear spacing to the edge of the slab, and especially if you have a tie down rod that's say 1.5 inches diameter, and it's only 2 3/4 inches from the edge of your slab, right? So this rod is so huge. By the time you put a washer on it, the washer actually sticks out from the face of the slab. And then, you know, good luck trying to get a rebar around there, right? Because you want to put some hairpins and, you know, breakout reinforcing. So what I've done is on some projects where I had particularly high loads is I've coordinated with the architect to have a larger edge of slab distance. And then I've also done localized enlargement of the slab edge just around the tie down that we integrate into the design. That way I can get it, you know, I can get clearance around all the rebar. So that's how I've dealt with that in the field. What was your other question, DePonch? That I'm.
So regarding the cambers, did have we seen any cambers that have come out? Did we have over camber situation with this?
Yeah. So cambering is all, you know, the jury is still out on that as well. Usually the problems, there have been problems, and they are related to the forms not being set at the right elevation. But as far as cambers coming out, I don't think we've had a problem with that. We've been very successful with that. And I think generally speaking, if your spans are, you know, 25 feet or something like that, it's not a big deal, especially if you were only going to call out a 1/2-inch camber or something, because those guys setting the formwork are going to put a little camber in by themselves anyway. But yeah, I think the jury's still out. We'll have to see.
All right.
Haven't seen those surveys yet. And then another, probably can have a whole separate, you know, magnitude 10 presentation would just be on detailing for podium depressions, because we've done that a bunch of different ways as well, and that can be kind of complicated. But generally, the builders, they want to have a flat soffit. Right? They don't want to slope their formwork or you know, do that. But if you have a flat soffit and you need a slab depression and you need a slope to drain, then your slab might end up getting really thick. So to keep that thickness down, then in your courtyard area, you might have to have a lot more drains, right? So that you don't have to build up as much to slope to drain. So that would be something that you want to coordinate early on when you start a podium project. Make sure you have adequate drainage, because you don't want to add those drains later. They do have a big cost impact. So, and when it comes to that, it's really good to have the concrete guy on board already. If you're part of a developer team that already has their contractor, then you'll be able to get their preference. Because I've run into contractors that had no problem with sloping the soffit, and others that won't do it. So it's really, there is a component of means and methods as far as how to best detail the slab for a particular project. On a side note, you know, we had the Lombardi project that was 3 levels subterranean and 2 levels podium above grade, with 5 levels of type 3 construction on top. That was the first podium project that I'm aware of that's ever been designed with fluid viscous dampers. So, you know, we designed it. The state was so excited about it. They had volunteered to pay for the seismic instrumentation. We had the dampers ordered, everything. And then suddenly and abruptly, the owner canceled the project completely, canceled the project. And now they're doing like a 30-story high rise on the same site. I was real excited about that one.
You know, we are doing a PT podium slab, and we ended up shaving about 1.5 to 2 inches of the thickness of the slab.
Is that Picasso?
No, that's for upland colonies. So we saved PT, and the contractor was very organized, so they only missed like a handful of anchors and a handful of hold downs, actually a couple of hold downs where we had him do X-ray and just do through bolts there. So it worked out for us.
That's great. So SAFE also has a detailing module, you know, they'll generate kind of rebar shop drawings for you, but I've never had enough time to figure out if it was any good. Maybe if somebody else ever goes through that, they can share what they find with the rest of us. All right, guys, if there's no other questions, I think we are done. If you have any specific Podium or SAFE related questions, feel free to reach out to me. If I don't know the answer, you know, I'm sure someone else in our talented engineering support group does have it. So don't be shy. We also have a support subscription with CSI, so we can always elevate, you know, complicated issues to them for support.
Good job, Phil. Excellent.
Thank you.
You've been doing, Joanna.
I did. I'll have more questions, but Danny and DeFont took them all from me.
If you excite a marketing team, I mean, you are something else.
The question, how do we get our banners hung on these podium projects then? Marketing applicable.
That's communications.
Oh,
the
a different group, huh?
Different group. Sorry, Zach.
That's it. Tracy, anything else? You're on the mute, Tracy.
Sorry about that. Phil, that was great. Thank you very much. I think I actually have a question or two I might take offline with you, but very informative. This is recorded, so we will have it posted, and I'll send you a link to where you can find that. And everyone, thank you for joining us for another Magnitude 10 and sharing your information and also being open to learn. Thank you.
Bye, guys.
Good job, Phil.